Hi, welcome to this particular module. In the last module, if you remember, what we have seen is components in microelectronics or MEMS based technology, where we were talking about microsensors, microelectronics, and then microactuators and microstructures. So, how they are interrelated, right. So, if you want to just quickly recall, if you see the slide, we talked about microelectronics, then that is considered as a brain that receives, processes and makes a decision, and data comes from the microsensors. So, when the data comes from the microsensors, it is processed through your microelectronic circuits, right. So, there are several domains in which people work and work on research ideas, and these are 4 domains within the MEMS, and each one has a significant amount of research involved. Microelectronics is where you design the circuits using cadence, right, and then further you have to fabricate it using the foundry, and microsensors is where you actually fabricate sensors. So, our part here is to understand about microsensors and microactuators. Now, when you talk about microsensors, the concept or the role of the microsensor is to constantly gather data from the environment. Suppose it is gas sensor, it will constantly get the data about the gas from the environment. If it is a pressure sensor, and if there is a uniform pressure applied, whether the pressure is increasing or decreasing, it will constantly measure the pressure. So, anything that is the sensor is meant for sensing, it should constantly gather the data and send it to the processing unit, and your processing unit is a microelectronic circuit. Now, the role is to pass the data to microelectronics. So, first is constantly gather data from environment, second is pass data to microelectronics for processing, and third one is that it can measure or monitor mechanical, thermal, biological, chemical and lot more, right. So, this is the role of the microsensors for monitoring several data from the environment. And finally, when you talk about microactuators, then it acts as a trigger to activate external device. Microelectronics will tell microactuator when to activate. So, first the sensor, the data goes from the microsensors to microelectronics. From microelectronics, the microelectronics will send the data to the microactuator to actuate, alright. So, and then finally, you have a microstructures. These microstructures are extremely small structures built onto surface of chip and built right into silicon of MEMS. We will be looking at the microstructures in a while. So, when you talk about fabrication process, alright, and today we will learn very important process called photolithography. So, in the fabrication process, the first step is that you have to deposit a film, right. So, if you remember, we have discussed about substrate. What is substrate? Anything on which we are going to fabricate the device, right. It can be silicon, it can be germanium, it can be glass, it can be metal, anything. So, substrate is a material on which we are going to design and fabricate the sensor or actuator or any other device. Now, let us say you want to fabricate a heater, right. So, you have a silicon wafer. If I have a silicon wafer, can I deposit another material on silicon wafer? Metal? No, because silicon is semiconductor. So, I had to have a insulating layer. So, if in that case we have an insulating layer, this insulating layer is SiO2, alright, and then on that we will deposit a metal. This metal is your nichrome, right. Nichrome is a material that you use for fabricating the heater. Now, how to deposit this metal for fabricating our heater? So, there where the deposition technique comes into play. In deposition, deposit thin film of material anywhere between few nanometer to 100 micrometers onto a substrate. If I deposit a film, the thickness can be from few nanometers to 100 micrometers depending on what kind of technology you are using to deposit the material. Then you have two kinds of deposition. the first one is physical deposition and second one is chemical deposition. So, in MEMS we call this as physical vapor deposition and chemical vapor deposition. Physical vapor deposition, also called PVD, and chemical vapor deposition, also known as CVD. All right. Two techniques to deposit a material onto the substrate, physical vapor deposition and chemical vapor deposition. In physical vapor deposition, the material is placed onto substrate. Techniques include sputtering and evaporation. We will see both the techniques. In evaporation further, if you want to, so if you see the film deposition, in particularly thin film deposition, then you have physical vapor deposition and then you have chemical vapor deposition, right. In physical vapor deposition or physical deposition, you have evaporation and then you have sputtering, correct. Now, in evaporation further you want to understand, then there is a process called e-beam evaporation, and another technique is called thermal evaporation. One technique is electron beam evaporation, the second technique is called thermal evaporation, all right. And sputtering is a mechanical way of dislodging the atoms and depositing a film. We will discuss about sputtering, e-beam and thermal in detail in few modules. So, the second process is your chemical vapor deposition. Chemical vapor deposition, what happens? If you see the slide, the stream of source gas reacts on substrate, stream of source gas reacts on a substrate to grow the product. For example, if you want to grow silicon dioxide, right, or you want to grow silicon nitride, right, then you can use the CVD technique. Technique includes chemical vapor deposition and atomic layer deposition. So, in chemical depositions you have chemical vapor deposition called CVD and atomic layer deposition called ALD. And in CVD further, if you want to understand, then there is LPCVD, then there is PECVD, right, LPCVD, PECVD. Low pressure chemical vapor deposition, plasma enhanced chemical vapor deposition. If you want to understand what are the substrates that we generally use in microsensors, then these are the substrates. The first one is silicon, second is your glass is also SiO2, third one is quartz, and then many more, all right, but most frequently used are silicon, glass and quartz. Alumina is also used. So, thin films examples are polysilicon, silicon dioxide, silicon nitride, metals and polymers, right. When you deposit a thin film of polymer, let us say P dot PSS is a conducting polymer. So, if I want to deposit a thin film of conducting polymer, I can use a CVD technique. If I want to deposit metal chrome gold, right, then I can use a PVD technique. You can use e-beam evaporation, you can use sputtering. If I want to deposit silicon dioxide, I can use sputtering or I can use PECVD or LPCVD. If I want to deposit polysilicon, again I can use sputtering. So, depending on what kind of film you want to deposit and the melting point of the material is very important, because that we will see why it is important. Particularly you understand in a two sentence or two lines, I am just showing it to you example. Assume that there is a film on this particular material, all right, and you have to deposit the film on the substrate. This is a source and there is a some metal on this source. So, let us put this key as a metal, this is a metal, okay. Now, you want to deposit this metal on my substrate. My substrate is, let us say metal got metal fell down, right. So, it does not happen when you actually deposit a film, okay. It will stay there because there is a boat, and then let us say this is a substrate on which you have to deposit a film. Now, for depositing this metal on this substrate, how can you deposit? You have to melt this metal, is not it. So, I have to melt this metal, right, such that it will evaporate from this source and it will get deposited on this substrate on the bottom, right. Here we want to have a deposition of this particular metal. So, to do that, what I have to do? I have to melt this. For melting this source, the material on the source, what we have to do? We have to heat this metal beyond its melting point, When you heat the metal beyond its melting point, what will happen? The metal will get evaporated, it will convert into vapor and it will be deposited onto the substrate. So, to do that, what you have understood, that the melting point of the source, the material that we are using on which you have the metal kept, right. So, this melting point of the source should be extremely high compared to the melting point of the material that you are going to deposit, is not it. The melting point of this metal and the melting point of the source, that is what we are talking about. The source is where you are holding it, okay. I am talking about this particular, let us say right now I am holding a mobile, but you assume that this mobile is a metal boat, okay, on which we are loading the material. Now, I want to evaporate this material. So, I have to heat this. So, the melting point of this material should be extremely high. So, then when this gets into molten form, this should not get affected, right. So, in that case, if I melt it at very high temperature, it will be evaporated and deposited on the substrate which is at the top of the vacuum chamber. We will talk about why we require vacuum and other things in the other module. So, the point is, I can deposit any material which has a lower melting point, significantly lower melting point compared to the source material, to the material of the holder, right. But silicon dioxide has an extremely high melting point. In that case, what can I do? I cannot use this technique where I am heating the material to its melting point, because the source material will also get the holder will also get melted, right. So, what I have to do? I have to go for another kind of deposition which is called electron beam deposition, where the heating would be done through the electron beam, but the material that we use at the bottom to hold the material to hold the source material is called crucible, right. In case of thermal evaporation, it is called boat. If you see this slide, this is a boat in thermal evaporation. I just give you an example, right. If you have material on the boat, if you heat this boat such that it reaches the melting point of this material, and high, then what will happen? This material will get melted and then it will start evaporating and depositing on the substrate, is not it. Now, the question is, if the material that is loaded into the boat has an extremely high melting point, or its melting point is equivalent to the melting point of the boat is a holder, this is a boat, okay. Then what will happen? I cannot use thermal evaporation, So, instead of that, I can use an electron beam evaporation, and as I just told you that in electron beam evaporation, the source material is loaded in a crucible. This crucible is made up of carbide or quartz or a very high melting point material, okay. In this crucible, I will load the material that I want to deposit, and then electron beam will be incident on this particular material, and the material starts evaporating. The cooling is done with the help of helium on the back side, okay, and then substrate will be coated with this particular metal. The advantage here is that the using electron beam, we do not require to actually worry about thermal evaporation, because we are not melting entire thing, only a part of it, and because of the electron beam intensity, this only the part of that material will get melted, and you have a cooling way from the back side, which is your helium, so that the crucible is not destroyed. Alright. So, we will discuss this about E beam evaporation in detail. I am just helping you out to understand that in case of thin film deposition, there are various techniques to deposit this thin film, right, and depending on what kind of film you want to deposit, silicon dioxide, silicon nitride, metal or polymer or polysilicon, you have to change that particular technique. When I should use sputtering, when I should use evaporation, when I should use CVD, right, when I should ALD. So, these concepts we will be looking at. Now, very important point that we need to understand is the patterning. Patterning is what? So, you remember, right, that we took an example of oxidized silicon wafer on which we have deposited nichrome, right. This nichrome we are depositing using a PVD technique. PVD is physical vapor deposition, and in PVD we are using electron beam evaporation to deposit this particular material, which is our nichrome. Alright. This is all cross section. Okay. If I draw it, it is like silicon wafer coated with oxide on which there is a nichrome. Right. If I have a cross section of this, it will look like this. So, once you deposit the nichrome on the oxidized silicon wafer, then what is the next step? What is the next step? You have to pattern this nichrome such that I will have a heater, right. I have to pattern the nichrome such that I can fabricate a micro heater. So, how to pattern this? Pattern this material. So, now you have a nichrome micro heater, and you have silicon dioxide, and further you have silicon, correct. If I draw the front view or top view will look like this, where I will have this material patterned in this form. If I take a cross section of this entire wafer, then I will have this particular, right. So, what is a patterning? Patterning is transfer of pattern into material after deposition in order to prepare for etching. Transfer of pattern. So, we will see what kind of patterning techniques are there. There are several ways of patterning it, but the most commonly used is photolithography, right. Photolithography. So, lithography comes from a word litho and graphic, which means that to carve from a single stone, lithos and graphic. Okay. So, now we will see how the photons or the UV light, in this case UV ultraviolet light, is used to pattern different materials onto the substrate. Alright. Now, let us see another term called etching. So, what is etching? So, you see, when I have a material, right, when I have a material, silicon dioxide, I have silicon, then I have my nichrome, right. Now, I need to protect my nichrome in certain area, and a remaining area I will want to etch it. Why? So, that finally what I will have, this protection we can use it photoresist. So, finally, what I want is the nichrome present only in this area, other area it should be removed. That removal is called etching. Okay. So, how can I protect this nichrome? By using my photoresist. How can I pattern my photoresist in this fashion? Using photolithography. Alright. So, using photolithography we can pattern the photoresist, and this photoresist will act as a mask against the chemical that is used to etch the metal below it or a material below it. In this case it is a nichrome, right. So, wherever the photoresist was there, you can see that nichrome is still present, is not it. Now, what is the next step? Next step is that if I dip this wafer, in nichrome etchant, what will happen? The nichrome where it is not protected by the photoresist will get etched. The nichrome which is not protected by photoresist will get etched, right. So, if I use a nichrome etchant which is a chemical, then that is called wet etching, right, because you are dipping the wafer in a chemical. Chemical is a solution that is used to etch the nichrome, right, and it is called the wet etching. So, wet etching is where we dip the substrate into chemical solution that selectively removes the material. What do you mean selectively removes the material? That means that it will not affect photoresist and it will only etch the nichrome, right. Now, process provides good selectivity, etching rate of target material higher than the mask material. What does that mean? That if you use silicon dioxide as a masking layer that will protect the nichrome below it, right, then this photoresist should not be affected. So, the selectivity of the metal or selectivity of the chemical should be extremely high. That means, it should only etch the metal and it should not etch the photoresist, that is called selectivity, alright. That is why it provides good selectivity, etching rate of target material higher than the mask material, right. Next one, instead of wet etching, if I use gases to etch the material, then it is called dry etching, because there is no wet component involved. So, dry etching is where you material sputtered or dissolved from substrate with plasma or gas variations. If I use two different gases such that it will affect the metal and the metal will get etched, is called dry etching, right. So, it is very easy. Now, for choosing a method, desired shapes, if you see the slide, you can see that there is a desired shape, etch depth, uniformity, surface roughness, process compatibility, safety, cost availability and environmental impact. When you choose the method, you should take care of all these parameters. If you go one by one, is what is a desired shape, right, because if I etch silicon wafer, if I etch silicon wafer from back side, I will have a 54.7 degree angle. If I etch silicon dioxide, right, from the back side to create this diaphragm, and this is my silicon dioxide, this is silicon wafer, silicon dioxide. If I etch it, then what I am getting? An angle of 54.7 degree. This is using wet etching, wet etching. But if I use dry etching, then I will have this pattern. So, what is the application? Are you okay with this 54.7 angle, or you want it to be etched in this particular shape, desired shape? If I want this shape, I will go for dry etch, right. This is what we call about desired shapes. Then second is etch depth, right. If I want to etch for, let us say, out of 500 micron silicon wafer, if I want to etch 400 microns wafers, right, and with uniformity, what kind of process should I use? I should select wet etching or dry etching. Next is the surface roughness. The roughness of this material, this wall, is very important in a lot of applications. So, what is the surface roughness of this wall? If I use wet etching, is it faster than dry etching? It is less costlier than dry etching, right. So, but what about surface roughness? Surface roughness will be better in dry or in wet. So, all these parameter we have to understand. Process compatibility, right, whether the wet etching the chemical will affect the photoresist or a masking layer, or dry etching will affect, right. When you talk about wet etching, again in wet etching there are several processes that are used for etching silicon. For example, if you talk about silicon, then there is a KOH, which is potassium hydroxide, and there is a tetramethyl ammonium hydroxide TMAH, which are used to etch the silicon wafer or silicon material. Now, if I use KOH and if I use TMAH, which one is advantageous? Again I need to see. The first is you have to select dry etching or wet etching, then within wet etching work under process, within dry etching work under process, right. So, next is safety. Which one is safer? If I have potassium hydroxide and if I have TMAH, both are wet etchants, which one I will use, right. So, I know that potassium hydroxide is faster, but TMAH is slower, but it will give me smoother edges. However, TMAH is neurotoxic, where KOH is not, right. So, if I have a proper fume hood, a good environment, everything is perfect, I am working in a class 1000 environment with a proper fume hood and proper wet benches, right, acid bench, solvent bench, everything, and then I am using a process, even the material is neurotoxic, it does not matter, because I am not putting my head. I have seen lot of people putting their head within the fume hood. It is not allowed. Fume hood is meant only to put your hands, not your head. Otherwise, why you require hood, isn't it? You have to put your hand and you have to work in the fume hood or in the wet bench. Any chemical process, please do not smell it, please do not put your head inside this particular equipment, wet bench, alright. So, then next is the cost. If I use dry etching and if I use wet etching, which is more costly, right. For most of the time wet etching is cheaper compared to dry etching is costlier. However, dry etching has its own advantages. Finally, environmental impact, the residual gases from the dry etching, right, will it affect environment more, or the residue gases with or the waste chemical after the wet etching, that will affect the environment more. So, that is another thing that we need to understand, alright. So, these are the things that you need to understand when you are patterning and etching. Now, let us see photolithography, very important topic. If you see the slide, photolitho, this is LITHO, lithography, alright, photolithography. We need to understand that what techniques we have to use for fabricating or for patterning the material, alright. So, for that what we will do, we have to use a polymer called photoresist, right, photoresist, alright. Now, photoresist is in short it is called PR. Okay. So, photoresist are of two kinds or two types, positive photoresist and negative photoresist, two types, positive photoresist and negative photoresist. Then next step you need to understand is called mask. Masks, two types, bright field mask and dark field mask, bright field mask and dark field mask. If I have this as a mask, this rectangle is my mask boundary, alright, and only this letters that I have written here, right, or these symbols that I am using, positive, negative, bright field, dark field, mask, PR, these arrows, these are only dark. Otherwise, my entire field, this one, this everywhere is bright, it is transparent. This is my bright field mask, this is my bright field mask, right. Instead of that, if I want to, if I have this entire box, alright, you assume I am just drawing lines, but you assume that everything is dark, everything is dark, right, everything here is dark, and only the pattern that I am drawing here, let us say this circle, this circle, these are bright, everything is dark, this all the checks is this is like dark, completely dark like this. Okay. And just I do not want to waste time in drawing the entire mask darker like this, right. So, assume that everything is dark like this, and in that only the circle that I have drawn, only the circle that I have drawn is bright, is transparent. This is your dark field mask, dark field mask. I will show it to you once again, the dark field mask, so that you understand that how it looks like. Now, what is the point of discussing about dark field or bright field, right. So, what is the point? You see, in bright field mask you will have the same pattern, you can replicate the same pattern which was there in the mask. What does that mean? So, if you see the slide, if I use a positive photoresist, alright, and I use a bright field mask, let us say we have this, this is my bright field mask. Okay. And then another one, this is my dark field mask. I will quickly draw it. So, you understand the role of the positive photoresist and negative photoresist in lithography. It is very important to understand this photolithography, because it is considered as a heart of any microsensors or microfabrication technique. Photolithography is considered as a heart of microsensors fabrication technique. All right. So, dark mask looks like everywhere it is dark except the pattern. Like this. So, now what I want to show it to you is that if I use a positive photoresist with my dark field mask and with my bright field mask, what will happen, and if I use a negative photoresist with my bright field mask and dark field mask, then what will happen. This is what it is, a dark field mask, right. Now, you can see it is a dark field mask, this is a bright field mask. So, bright field, dark field, field FIELD, FIELD, dark DARK, right, like that. Bright, you know, bright, 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 field, FIELD, bright field, dark field. Okay. Now, if I use positive photoresist and if I use bright field mask and dark field mask like this, then what kind of pattern I will have on silicon wafer. So, this is a silicon wafer, all right. Then here, so if I let me just draw a rectangle substrate, it becomes easier for you to understand, rectangle substrate like this. All right. Then when I use bright field mask and positive photoresist, then I will have this pattern. When I have positive photoresist and dark field mask, then I will have this pattern, the one that I am drawing. So, what you see is that whatever pattern was there on the mask, whatever pattern was there on the mask is same, the same pattern is transferred onto the substrate, right. You see the dark field mask, how it was looking, it was looking same like what I am drawing here. The same pattern is transferred or is retained onto the substrate, onto the substrate. That is the advantage of using positive photoresist, or that is the role of positive photoresist, or you can say characteristics of positive photoresist, that it will retain the same pattern as on the substrate, right. See, this is what I will have if I use my positive photoresist. This is my substrate, okay, substrate. So, if I use my bright field mask, I will have the same pattern. If I use dark field mask, I will have my same pattern, but this is for positive photoresist, this is for positive photoresist, right. Instead of that, if I use negative photoresist, negative photoresist. So, if I use negative photoresist with bright field mask, right, what I will have is this kind of pattern, and if I use negative photoresist with dark field mask, I will have this pattern. You see, opposite. If I use positive photoresist, so let me just draw positive photoresist with this kind of arrow or dotted arrow. If I use positive photoresist, I will have this pattern, and with this mask I will have this pattern. But in case of negative photoresist, if I use bright field mask, I will end up with this. If I use a dark field mask, I will end up with this pattern. So, what we understand? We understand that I told you, right, there is a UV light that we are using it in photolithography. So, here what you understand is that when I use positive photoresist, then the area which is not exposed, you see, let me just remove this arrow for the negative, so it is not confusing for you. Now, you see here only for positive photoresist, okay, we are talking only for positive photoresist. In case of positive photoresist, the area which is not exposed by UV light, the area which is not exposed by UV light will be stronger. You can see here this area is not exposed, so it becomes stronger. This area is not exposed, it becomes stronger, correct. Now, in case of negative photoresist, if I talk about negative photoresist, then the area which is not exposed, becomes weaker, right, and the area which is exposed, right, will become stronger. You see, this area is exposed, this transparent thing is exposed. So, we have here this pattern. In this case negative photoresist, I am talking about negative photoresist. In this case bright field mask, the area that is exposed and the area that is not exposed will be weaker, you can see here, right. That means that if I am using positive photoresist, then the area which is exposed and the area which is unexposed, exposed and unexposed is with respect to UV light, right. So, in case of positive photoresist, the area which is unexposed gets stronger, the area which is exposed becomes weaker, okay. In case of negative photoresist, the area which is not exposed becomes weaker, the area which is exposed becomes stronger, right. Easy, this is very important to understand. Okay. That is why we are talking about this, extremely important to understand how you are using or when you will have to use a bright field mask, dark field mask, how the area which is exposed, what kind of pattern you will get, if the area is not exposed with UV light, what kind of pattern you will get. So, extremely important to understand bright field mask and positive photoresist, dark field mask and positive photoresist, bright field mask and negative photoresist, bright field mask, dark field mask and negative photoresist. Now, very simple concept is, whatever the pattern on the mask is there, same pattern you can transfer on the wafer or substrate when you are using positive photoresist. But when you are using a negative photoresist, then whatever the pattern is there, the opposite pattern will come on the substrate, alright. So, in other way, positive photoresist, area which is not exposed becomes stronger, negative photoresist, area which is not exposed becomes weaker, positive photoresist, area which is exposed becomes weaker, negative photoresist, area which is exposed becomes stronger, right, very easy, extremely easy to remember, alright. So, what I feel is, now let us end this particular module here and we will continue in the next module, where I will talk about the process that we use to pattern the wafer. What are the process, right? We will take one example and so that you understand, we will take very simple example of a heater, right, so that you get the point that what kind of technique or what are the processes involved, what are the steps involved in photolithography, right. Till then you look at this module, if you have any questions, ask us through the NPTEL forum and we will be able to answer your queries, right. Till then you take care, I will see you in the next module.